Hello everyone, this is lecture 10 of ComSci 123, Binary Search Trees. In today's video, we will talk about binary search trees and look at several balanced search trees like the Splay Trees, AVL trees, red-black trees, and the 2-4 trees. Okay, so let's start. So in our discussion of the BST or the binary search tree, we will follow this outline. So first, we will give the motivation as to why we need BSTs. And then we'll introduce what binary search trees are all about. And then we'll take a look at how to do search, insert, and delete in BSTs. And finally, we will also discuss the performance of the BSTs. Okay, so let's start with the motivation for BSTs. So far, we have seen several ADTs that model a searchable collection of entries. And if you recall, entries are just key value pairs, right? So we've seen two ADTs so far that model such a collection. So we have the map and the dictionary. And if you remember, the only difference is that for maps, you need to have unique keys, whereas in dictionaries, you can have same keys are allowed. Okay, so both of them model a searchable collection of entries. And we've also seen several implementations of maps and dictionaries already. So let's try to remember what was the best possible implementation so far. So first, we tried to use an unsorted array, okay, to model or to implement our maps and dictionaries. Now, since the array is unsorted, when we want to look for the key, then we will have to do linear search, right? So for search, that would be O of n for the linear search. Same for delete, right? Before we can delete the key, we need to do linear search also. And when we insert to the map, if it's unique, then we have to do linear search also to make sure that the key does not exist already. But if it's a dictionary, if the keys don't need to be unique, then we can just add it at the end, right? So it's constant time. But everything else is O of n or linear time because we need to do linear search, right? And additionally, for delete operation, it also needs to have shifting of entries because when we delete an entry at the middle, then it will leave a hole. So we need to shift entries to fill that hole, right? So remember this one. If we used a DLL instead of an array, but it's still unsorted, then we will at least improve on the shifting of entries because, of course, for DLL, you don't need to shift entries. You just need to relink the nodes, right? But since the DLL is still unsorted, then we'll still have to do linear search, right? So search, delete, and insert still runs in O of n. So we only really improved on the shifting of entries here. But since it was unsorted, the bottleneck was still the linear search. Now, we also tried to use a sorted array. Okay, so we sort the entries according to their key. And if we have a sorted array, then we can use binary search. And that would make the search faster because it will now run in O of log of n. Okay. For deletion, we can also do search in O of log n. And for insert, we can also do the search in O of log n. But the problem is, since it's still an array, we still need to do the shifting of entries forward or backward, either to make room for the insert or to fill the hole after deletion, right? So we will still need to do shifting of entries. That's why even if you have O of log n search, you will still have O of n running time at the worst case because of the shifting. Okay, so it's still bad. We also discussed hash tables and skip lists. But for hash table, the performance really is dependent on the hash function quality. So if you have a good hash function, then it will give you good distribution of entries. But if you have a bad hash function, then it will also have a bad performance. And it also depends on the load factor. So how full is the hash table? So if it's close to full, then it will also give you a lot of collisions if you're doing linear probing, right? And for the skip lists, the performance also depends on the random heights of the skip list towers. So there is a dependence on either the hash function quality or the random heights. So we're not really assured of the actual running time. Okay, so either we have linear time for the linear search, or linear time because we're using an array, or we're depending on some external factor like hash function quality or random heights. So we're still not satisfied with the current implementations for searchable collection of entries. So that is where your binary search tree will come in. Okay, because binary search tree, at least the goal is to do search, delete, insert in O of log n time. Okay, so all three operations can be done in O of log n time, which is huge because not one of those implementations that we've seen so far can do this consistently. Okay, so now why is this important to have log of n time? Okay, so let's say that you have a billion entries already in your collection. Okay, so if you have linear time, then of course you also have 1 billion steps every time you do an operation, okay, at the worst case. But if you have log of n time base 2, then you only need 30 steps. So you can see that the big disparity between a billion steps and just 30 steps. Okay, so the advantage is you can do faster search, insert, and delete because you have a lower order running time, which is log of n. Okay, so that is our motivation for why we need another implementation for searchable collection of entries, which is the BST. Okay, so let's now look at binary search trees or BST. So it's not BTS or BSP, it's BST. Okay, so let's see what binary search trees are. So binary search trees are, well, binary trees, and within their nodes they store entries because, as we said, they will try to model a searchable collection of entries, right? Now BSTs have this one property. Okay, so let's say you have a node, so all the keys to the left of the node, okay, will be less than the key of the node. Okay, so all the keys to the left should be less than the key of the node, and all the keys to the right should be greater than the key at the node. Okay, so to the left everything is less than, to the right everything is greater than the node. And it's not just limited to the left child and the right child. Okay, everything in the left subtree must be less than the key of the node, and everything in the right subtree of the node should be greater than the key of the node also. Okay, so yeah, it's not just limited to the left child and the right child. Everything in the subtree should be should follow this property. Okay, so this is actually named after the binary search algorithm because, as you'll see later on, it will kind of mimic the behavior of binary search. Okay, so we've seen a similar kind of binary tree, which was the heap in the previous video. Now, how is this different from the heap? Okay, so for the heap, the heap property was that if it was min heap, is that the node's key should be less than the children, right? So you have here for our heap, the min node should be at the root, okay, and then the children should have less than the the node should have less than the children. So 1 is less than 2 and 5, right? And then for 2 here is less than 3 and 4, and then 5 is less than 6 and 7. So that was the property of the heap, right? So node should just be less than the children. But for the left child and right child, you don't have any restrictions. But here in the BST, it has a strict restriction. So the left should be less than the node, and then the node should be greater than the node should be less than the right. Okay, so left is less than node, node is less than right. Okay, so you have 2 is less than 4, and then 4 is less than 6 right here. But everything on the left subtree should also be less than 4, so this should be less than 4, and then everything on the right subtree should be greater than 4 also. Okay, so you can check. Okay, so that is the difference between the BST and your heap. Okay, so let's try to figure out for each binary tree here if it's a BST or not. Does it follow the BST property or not? So you can try to pause first and try to figure it out before I go to the next slide and show you the solution. Okay, so I think we'll have about 10 binary trees for this exercise. So Just try to follow along. So is this a BST or not? Well, for this one, this is a BST. So everything follows the BST order. Now, how about this one? Is this a BST or not? Well, this one is a BST. Okay, so you can check for yourself and verify that it is indeed a BST. Now, how about this one? Well, for this one is not a BST because you have a violation here. So 12 is in the left subtree of 10, but 12 is greater than 10, right? So everything to the left of 10 should be less than 10, but 12 is greater. So this is a violation. So this is not a BST. Okay? How about this one? This one is valid. Okay, so instead of the 12 here, if we had the 6 instead, then that is valid. How about this one? Is this a BST or not? Well, it's invalid because you have this violation here. So for example, 8 has a left child 9, but 9 is greater. So that is a violation, right? So this is not a BST. How about this one? Well, this one is invalid because of 11 here. So 11 is in the left subtree of 10, and 11 is greater than 10, so that is that doesn't follow the BST property. How about this one? This one is valid. Okay, so you can check for yourself, but that is a valid BST. How about this one? This one is invalid because of these two nodes here. So 15 actually falls inside the left subtree of 14 because you have, it's part of the left subtree here, right? So everything to the left of 14 should be less than 14, but 15 is obviously greater than 14, so this is a violation. Okay, so that is not a BST. How about this one? Well, we have more violations. So we've already seen the 14 and 15, but let's see the other side. So for this one, 99 is right here, and so everything to the right of 99 should be greater than 99, but these are all less than 99, so these are violations. Okay, so this is not a valid BST. Now, how about if we put 99 to the root? So is this a valid BST or not? Well, it's even worse this time because everything on the right subtree this time will be a violation, right? So everything here violates the BST property because everything here should be greater than 99. But as you can see, all of them are less than 99, so all of them are violating the BST property. Okay? So yeah. So try to practice figuring out if the binary tree is a BST or not. Okay, so just check each node. Does it follow the node is greater than the left child, and then the node is less than the right child, and then try to do that for all subtrees also. Okay, so with practice you can try to figure out with ease if it's a BST or not. Okay, so let's take a look at more BST properties. So for your leaf nodes, you'll actually see something called the null nodes. So earlier, if you've noticed, there are squares here that I put at the nodes without children. So if it's a leaf node, like for example 3 is a leaf node because it doesn't have any nodes that contain keys, then we will actually add null nodes to it. So null nodes are nodes that doesn't contain anything, so it doesn't have any entry. They're just there as placeholders. Okay, so our leaf nodes are actually null nodes. So those are the squares that you can see here. Okay, if you want the leftmost node, if you want the min key, you go to the leftmost node of the binary search tree because that will give you the minimum key. If you want the maximum key, you go to the rightmost node. Okay, so I'll show you that in the next slide. And if you do the in-order traversal on the BST, then it will give you the ascending order of the keys. Okay, now keys in the BST can be unique or not depending on whether you are modeling a map or a dictionary. But for the purpose of this lecture, we'll assume that the keys are unique in our BST so that it's simpler. We don't need to do some special cases if it's already existing or not, or if it's like instead of just less than, it will be less than equal. So we'll just assume that the keys are unique, but the adjustment for when keys are not unique is pretty simple. Anyway, okay, so the rest of the discussion should still work even if the keys are not unique. Okay, so we've said that leftmost is at the min, rightmost is at the max, and when you get when you do the in order traversal, you get the ascending order. So let's see that here. So if you go to the leftmost, so from the root you go left, then left, so this is the leftmost, so you get the min node. And then if you go right, keep going right, you'll get the rightmost node, which is the min and the max nodes respectively. Then same here, leftmost is 1, so that's the min, rightmost is 9, so that's the max. And then if you do the in order traversal, so you have the 1, 2, then 3, and then since this left subtree is done, you go to the root, which is 4, and then you go to the right subtree, so 5, 6, and then 7. So remember, in order traversal is left, and then node, and then right. Okay, so if you do that here, we'll go to the left subtree first, so that's left is 1, node is 4, and then 6, and then the middle node, which is 7, and then the right subtree, which is 9. So 1, 4, 6, 7, 9. So you'll notice it's in ascending order if you visit them in the in order traversal. Okay, so those are BST properties that you need to know. Okay, so let's now go to the three methods, so search, insert, and delete. So let's start with searching in the BST. So when you search for a key K, it's kind of similar to binary search. Okay, so you'll start at the root. Okay, so if you have found the key, okay, so if the key of that node is already the key that you're looking for, then return it because you've already found it, right? If the key that you're looking for is less than the node's key, then you go to the left, okay, because you know that everything that is less than the node's key is to the left subtree. Okay, if it's greater than the node's key, then you go to the right. Okay, but if you reach a null node, then you return the null node because you know that the key that you're looking for is not found. Okay, since you've reached like a dead end. Okay, so you're sure at that point that the key that you're looking for, key K, is not found. Okay, and then continue doing this if you haven't reached a return, a stop condition. So go back to step 2. So after going left or right, check again if that is already the key that you're looking for, and then go again to the left or right, and so on. Okay, so you repeatedly do this steps to find the key K, or you end up with a null node, and then you also stop there. Okay, so it's pretty simple. So if you search for 76 in this BST, so you'll start at the root node. Okay, so for this one, 76 is greater than 44, so we'll go to the right. It's less than 88, so we'll go to the left. It's greater than 65, so we'll go to the right. It's less than 82, so we'll go to the left, and then we have found the node 76. Okay, so it's pretty simple, right? Now next, let's try for 25. So again, we'll start at the root. 25 is less than 44, so we'll go to the left. 25 is greater than 17, so we'll go to the right. It's less than 32, so we'll go to the left. It's less than 28, so we'll go to the left again. But then we've reached a null node, so we know that 25 is not found, so we'll stop here and return the null node. Okay, So if you don't find the search key, you return the null node, because if 25 was here, this should have been the position of 25, right? Because 25 is less than 28, right? So it should have been here. But since it wasn't there, then we'll just return the null node, which is where it's supposed to be. Okay? So that is how BST search works. So it's pretty simple, right? Okay, so how about the performance of search? So at each node, you only really do constant time, because you're just comparing if it's equal, less than, or greater than, and then updating the node after that. Okay? Now the worst case is if you do the iterations from the root all the way to the bottom depth, right? So from the top level all the way to the bottom level. So that's the worst case. So the search running times worst case is O of H, where H is the height of the tree. So if you go from the root all the way to the bottom, that is equal to the height of the tree. So the running time of the search is O of H, so proportional to the height of the tree. Okay? So that is search. Now how about for insert? If you want to insert the key K and the value V, then first we will need to do search. Okay, so it's important that you understand how search works, because for insert and delete we will use search always. Okay, so please make sure that you understand how BST search works first before proceeding with insert and delete. Okay, so going back, before inserting, you need to do search for the key K. It will either return a node or a null node. So if it returns a node, that means that the key K already exists, right? If it returns a null node, that means that it doesn't exist and we can add it. So since we said that we're modeling a map here, so the keys should be unique. So if we have found that the node of the key is equal to the key that we're inserting, then we'll just overwrite, okay? Because the key value, the key already exists in the map, okay? But if it's a null node, that means that it doesn't exist yet, okay? So we will insert that entry into that null node, okay? So it's safe to add because it doesn't exist yet, okay? So search, if it's found, overwrite. If it's not found, then insert the entry to the null node, okay? So let's see an example. So let's try inserting 8. So the search will proceed as follows. So 44, 8 is less than 44, so it will go to the left. It's less than 17, so it will go to the left. And it found a null node, so it will insert it here. So 8 is inserted to the left of 17. Okay? It's pretty simple, right? Now how about if we insert 68? So following the search path, it will go to the left, to the right. So 88 is greater, so go to the left. And then 68 is greater than 65, go to the right. Less than 82, left. And then less than 76, so left. And then we found a null node, so this is where we insert it. So from 76 with a null left child, 68, which is what we inserted, will be the new left child of 76. Okay? So it's pretty simple. Search and insert it when you find a null node. But if you find the actual node that you were looking for, like for example in here when we insert 82, so we'll find 82 here, so we'll just overwrite it. We won't add a new entry or a new node if we are modeling a map, so we'll just overwrite. Okay, so you'll notice 82 was still here and no new node was added. Okay, so that is BST insert. Now how about the performance? Now first we needed to do search, and as we mentioned earlier, search runs in O of H, which is proportional to the height. The actual insertion itself takes constant time because you'll just add a new node and connect it to the parent, right? So the insert worst case running time is O of H because the search is the bottleneck. Okay, so you're doing search beforehand, so you have the overhead of O of H. So bottleneck of your insert is actual search. Okay, so insert also runs in O of H because of the search. Okay, so let's now move to the last method, which is the deletion. Okay, so if you want to delete key K, what will you do? First, you'll still need to do search, right? So before you can delete this key, I have to look for where this node is in the tree, right? So I'll search for the key K using our search procedure earlier, and whatever node is returned, I'll call that node X because I will be deleting that. Okay, so I will exit out. So if it's not found, then there's nothing to delete because the key does not exist in the tree. But if it's found, then we'll have to check the 3 cases for deletion. Okay, so what are these 3 cases? So we have the 3 cases here for deleting. So case 1 is if node X doesn't have any children, so it has only null nodes. Case 2 is if it has one child. Okay, we'll call that child C. And case 3 is if it has 2 children, so this unnamed nodes here. Okay, so let's go through each case to see what we'll need to do in each one. So for case 1, this is when the X has no children. So if it only has null nodes as children, then that is case 1. So what will happen? So since it doesn't have any nodes that contain keys, then it's safe to just delete this node and replace it with a null node. Okay, so that's what we'll do. Replace node X with a null node. So we can just remove this and replace it with a null node. Okay, so pretty simple. So an example of that is if we delete this one is when we don't find 7. Okay, so if we don't find 7, so the search will end in the null node here, so we know that 7 does not exist, so there's nothing to delete, so the tree remains the same. So this one is the example for case 1. If we delete 8, so we found 8 here, and we notice that 8 doesn't have any children, right? It only has null nodes, so it's safe to delete 8. And when we delete this, we'll just replace this with a null node here. Okay, so the new tree will now look like this after deleting 8. Okay, so it's pretty simple if it doesn't have any children. Okay, now how about if we delete 78? So the search will bring you all the way down here, and 78 doesn't have any children, so it's safe to delete this and replace it with a null node here. So 80 will have a new left child of with null node. Okay, so that's pretty simple. Now how about the second case? So the second case is when the node X has one child node. So it could be the left child or the right child, it doesn't matter. So as long as it has one child node, so what will we do? So either the X node, which is what we'll need to delete, has a left child and then the right is null, or the left is null and then the right is a child node. So what we'll do here is, well, since it only has one child, we can actually just replace this node X, which we will delete, with the child node. So we'll kind of like elevate the child node or promote it, right? So from here, since you're the only child anyway, when the parent goes away, you can just replace it. So P's left child was X before, and then when we remove this, P's left child became the child C. Okay, and then you can do the same if it was the right child. Okay, so X, when we remove this, we have the right child, which is C. So when we remove it, the P can just connect here to C. Okay, so we can just replace node X with the child node because you can think of it this way, like you're the sole heir of your parents, so the business of your parents will have to go to you, so something like that. So just replace the node X with the child node. And I'm showing here that it's X is a left child, but they should be symmetrical if X is a right child also. Okay, so it doesn't really matter as long as it's X that has one child, so just replace it with the child node. Okay, so let's see that in an example. So let's try to delete 97. So in here, 97 is found here, and 97 has one child, which is 93. So when we delete 97, we'll just promote 93 here, so 88 will actually have 93 as its new child now, right child. Okay, so it looks like this after deletion. Okay, So how about if we try to delete 28? Okay, so if we try to delete 28, so we'll find 28 here, and we find that it has one child, which is 29. Okay, so after deleting 28, we'll just replace the deleted node with the child, which is 29. So 32's new left child will be 29. So that's why you have that one here. Okay, so yeah. And finally, we have another example, delete 32. So if we delete 32, we find that node here, right? And it has one child, 28, because the other one is a null node. So we'll replace 32 with 28, so it will be like this after we delete this. And you'll notice that it was not just 28 that was elevated, but it's the whole subtree of 28, right? So the whole subtree of 28 was elevated here. So we just removed the node here and relinked the parent's right child to 28. So now the descendants of 28 will also follow, right? Because we only linked this one. Okay, we don't know whether that has more children there or not, but as long as we have relinked the children with the old parent, then everything will follow as well. Okay, so it's not just the one child, but the child's subtree. Okay, so that is case 2 for deletion. And then on the other side, if we have 82, we have another example. 82 has one child, which is 76. So the whole subtree of 76 will be elevated, right? So it's the whole subtree of 76 here. That will be the new right subtree of 65, which is here. So you'll notice after 65 you have 76, and then after 76 it still has the same subtree right here, which is 80 and 78. Okay, so yeah, that is the examples for case 2 of deletion. And finally, we have the last case, which is case 3, and this is when the node X, which is what we'll delete, if it has two children nodes. Okay, so what will we do? So for this one, first I'll tell you the steps, and then I'll explain why we need to do the steps in the next slide. Okay, so if it has two children nodes like this, so X has two children nodes, right? So what we'll do is we'll try to find the next node. So what is the next node? So you do this by going right once and then keep going left. Okay, so right once and then left all the way until you reach a dead end. Okay, so if you find this next node, like let's say this one here, then we will copy this node's item to X. Okay, so the item here will be copied to node X's it will be overwritten. So you'll notice the item of new node is already here, and then this new node is what we'll delete. So this one will be deleted. Okay, so those are the steps. So find the next node by going right once, then keep going left. So that's the next node, and then you copy the next node's item to node X, and then once you have safely copied it, you delete the next node. Okay, now let me explain why we need to do these steps. So the next node is actually the in order successor of the deleted node. So this is the node with the smallest key that is greater than the node's key. So it's a successor, right? So it should be greater than the node's key, and it's the next successor, so it should be the smallest key greater than the node's key. So if it's like 1, 2, 3, 4, 5, if that's the in order traversal, if you're deleting 3, the in order successor is actually 4, right? So it's the smallest key that is greater than 3. So everything here is greater than 3, but this one is the smallest. So that is the next node. Okay, so basically the next one in the in order traversal. Okay, so that's why we need to do the we need to go right once, because in the right subtree, that is where you'll find the keys that are greater than the node, right? and then keep going left because you want to go to the leftmost part of the subtree wherein you'll find the smallest key or the mean key, right? So the smallest key that is greater than the node's key. So go right to the right subtree and then keep going left to go to the leftmost part to find the smallest key. Okay? And we are also assured that the next node that we'll delete will be either just case 1 or case 2. Why is that? Because okay, so when we found the next node here, we are assured that the left child of the next node is a null node. Why is that? Because if this was another node here, then we should have gone to this node because we'll keep going left until we reach a dead end, right? So we are assured that the left child of the next node is a null node. So this is already sure, right? Now the right child we don't know. So this could either be a null node also, right? In that case, that would be case 1 because then the next node would be having no children, right? But if it's another node here, then that would just be case 2. Okay, so it either has the next node either has 1 children or none. Okay, it can't have two node children because we're assured that the left child at least is already a null node. Okay, because we can't keep going left anymore, so we were stuck here. Okay, so yeah, so it's either case 1 or case 2, and then we repeat for the deleted node. Okay, so we cannot just delete the node X with 2 children just like what we did in case 2, because if we do that, then the 2 children would be orphaned, right? So that's why we need to do the switching. Okay, and we also cannot just replace the node X with either of the children's item because it will break the order of the BST. So I'll show you that in a while. And by replacing the deleted node with the next node's item, then we will preserve the order of the BST, just like this. So that is because for this one, the next node is, so go right once and then keep going left. But if you go left here, it's already null, so we'll stop at 5, right? So this is the next node. And it makes sense to replace 4 with 5 after deleting 4 here, because in this order, everything to the right of everything to the left of 4 is less than 4, right? And everything to the right is greater than 4. Okay, if you replace that with 5, that still makes sense, right? It's still less than 4, still greater than 4. Okay, so that one is still kept, and that's also less than 5 and greater than 5. Okay, because they are successive, right? So yeah, that is why the next node works. So go right once and then keep going left. So doesn't matter how many lefts you go until you reach a dead end, until you reach a null node. Okay, so that is using the next node. Now, what would have happened if we replaced it with the children? Okay, so what if we deleted 4 but then we replaced it with not the next node but the left child, for example? So if we elevated the left child, then there will be a violation, because here 3 was on the right of 2, so this one is greater than 2, right? But if you elevate 2 here, then 3 is still on the left subtree, but it's greater than 2. So this is wrong because everything that's greater than 2 should be on the right subtree, right? So this is a violation. And then if you do the same with 6, there's still a violation, because if you look at 5 here, it's part of the right subtree of 6, but 5 here is less than 6. So that is a violation because everything that's less than 6 should be on the left. Okay, so it doesn't make sense to replace it with the children. It makes sense to replace it with the next node. Okay, or you can also alternatively use the previous node. Okay, so instead of the in order successor, you can also use the in order predecessor, so it works fine as well. So this is the node with the biggest key that is less than the node's key. So it's the opposite, right? Here's the previous. So instead of going right and then keep going left, we'll go left once and then keep going right. So it's the opposite of what we did earlier. So we go left because we want to go to the left subtree where the keys are less than the node, and we keep going right because we want to go to the rightmost part of the subtree wherein we get the biggest key. Okay? So previous node also works. Like, so go left and then keep going right. So the previous node is 3, and then you replace that with you swap it with delete node here. So 3 is already here, and then you delete this one. Okay, so previous node also works, but for this lecture we will just use the next node, okay, for consistency. So I'm just telling you that previous node would have also worked. Okay, so that is the 3 cases for BST deletion. So let's take a look at an example for the third case. Okay, so if we delete 88, find or search will find it here, right? So search will find it here. So you'll notice 88 has 2 children, right? 65 and 97. So we'll have to use case 3. So we'll go to the next node. So go right once and then keep going left. So if we go left, we'll encounter a null node, so we'll stop here. So 93 is our next node. So we'll copy the value of 93 to the del node, which is 88. So this will have 93 here. So you have 93 here. And then we'll delete this node. And since this node is only has null children, then this will be case 1, right? So just an easy deletion, we'll just replace it with a null node, and then 93 has been copied over to where 88 was. Okay, so yeah. Let's see another example. This time, what if we delete 65? So the search will find 65 here, and looking at its number of children, it has 2, 54 and 82. So we'll have to use case 3 still. So for the next node, go right once and then keep going left. But if we go left here, we'll encounter a dead end. So 76 is our next node, right? So 76 value will be copied here to 65, which is overwritten, and then we'll delete this node here. Okay, so if we delete this node, it has 1 child, so this will be case 2. So 80 will replace this node here. So after 82, we'll have 80. So that's why 82 and 80 are connected here. Okay, so after doing case 3, the next deletion would be either be a case 1 or a case 2. Okay, that is assured. So yeah, those are the examples, and then we'll have one last example. What if we delete the root node this time, right? So delete 44. So we'll find 44 at the root node. Well, it still has 2 children, 17 and 88. So we'll still use the case 3 here. So go right once and then keep going left. So go left, and then if we go left, we're stuck. So we'll stop at 54. So 54's value is added here, and when we delete this, it's a simple delete because it only has null nodes, right? So null nodes only. So that's case 1. So we'll just replace it with the null node. Okay, so yeah. So I hope you understand how to do deletion. Whether to use case 1, case 2, or case 3 depends on the number of children of the node that you're about to delete. Okay, so how about the performance of delete? So first we need to do search, right? So to find the actual node that we're going to delete. So it's still O of H. The actual deletion takes O of 1 because you're just either replacing the deleted node with a null node, or replacing it with a child node, or if in the case of case 3, finding the next node's worst case could be O of H because you could be searching from the root all the way up to the bottom level, but that is additive to the search. So that is O of H plus O of H. So if it's 2 times O of H, that's still O of H, right? So the worst case of deletion is still O of H. So it's still dependent on the height of the tree. Okay, so still search is the bottleneck. So for both insert and deletion, the actual deletion or insertion is fast, but the search is what keeps you in O of H time. Okay, so that is the performance for deletion. Okay, so let's try to create BSTs from scratch. Okay, so starting with an empty BST, we'll try to insert the following keys. Okay, and notice that I said that we're modeling maps that has key value pairs, but I'm only using the keys because the values actually don't matter in the comparison anyway. So to keep the illustrations simpler, I'm just using the keys. But just know that the entry is being stored inside the nodes. So that's both the key and the value. Okay, so starting from an empty BST, if we insert 11, it becomes the root. If we insert 5, it becomes the left child of the 11, right? Because it's less than 11. And then if we insert 8, it will be inserted here in this position. If we insert 16, it will be inserted in this position. If we insert 4, it's here. 19 is here. And 17 is here. So you can pause the video and try to figure out why that is. Okay, so given the current structure of the tree, for example here, in the last one, if we were to insert 17, then we'll do search 17 here. So that would be here, and then 16, 17 is greater than 16, so we'll go to the right child, and then it's less than 19, so we'll go to the left child. So that's why we need to insert 17 here. Okay, so with this ordering of the insertions, we have this tree right here. But what if we had a different insertion order? Like what if instead of starting with 11, we started with 5? So if that's the case, 5 will become the root, and then if you insert 8, it will be here. If you insert 16, it will be here. 4 will be here, and so on. So if we follow this order, this is the tree that we're producing. Now if we started with 16, 16 becomes the root, and this is the tree that we are going to produce if we follow this order. Now if we follow this order right here, then the tree becomes balanced, right? So if we start with 11, it becomes the root, and then 5 becomes left child, 17 becomes the right child, 4 becomes the left child of 5, 8 becomes the right child of 5, 16 here, and then here. So out of the trees that we have created, this one looks the most balanced, right? And it also has the shortest height. Okay, because the height of this is 1, 2, 3, right? So 1, 2, 3, that's the maximum height. So height of 3. For this one, you have 1, 2, 3, 4. Same with this one, it also has a height of 4. And then for this one, it only has a height of 2, right? So 1, 2. Okay, so this one looks like the perfect order. Now, how did we come up with this perfect order to have a perfectly balanced tree? Well, so the way that we did that was we followed the binary search order, basically. So start at the middle. If you have the if you rank them in ascending order, start at the middle, so that's 11, so that's the first one, and then you go to the middle of the left, so which is 5, so that's the second one, and then the middle of the right, which is the 17, so that's the third one, and then repeat the process with the left one. So the left middle, and then the right middle, then the left middle here, and then the right middle here. So that is the order when you do the binary search, right? So that is the perfect order if you want the balanced, perfectly balanced BST. Okay, but what we can take away from this is that if we have different insertion orders, we'll produce different structures for the tree, even if they are the same set of keys, right? So that's the same. That's 4, 5, 8, 11, 16, 17, and 19. It's just that the order was different, and so we produced different trees because the root node will be different according to what node you inserted first. Okay, so that is our main takeaway from this slide. So insertion order affects the tree structure. Okay, so if you talk about the general performance of the BST, the search is very efficient because you recursively proceed to one subtree only, right? It's either the left or the right, and so if you go to the left, then you can just disregard or discard the right subtree totally, because you know that the key that you're looking for is not there, right? So if it recursively proceeds to one subtree only, then the search will be faster. And you also don't have any shifting of entries on insert and delete, unlike in arrays, because this is a tree, right? So there's also that advantage. And as we said earlier, all of search, insert, and delete will run in O of h time, which is the tree height, because search is the bottleneck. So because of search, insert, and delete also runs in O of h. Okay? But what can we say about the height of the tree with regards to the balance? Okay, so in relation to the balance of the tree. So let's see if we have a full BST and if we have an unbalanced BST. So if we have a full BST which is perfectly balanced like this, so we have 7 entries here, 7 keys. So the log of 7 is log of 7 base 2 is about 2.8. So if you have minus 1, that would be around 2. Okay, so the height of the tree here is 2, which is O of log n, because it's log n minus 1. Okay, but if you have a very unbalanced tree that looks like this, then the height would be O of n, which is n minus 1, which is 6, right? So you have 1, 2, 3, 4, 5, 6. That is your height. And how did we actually produce this very unbalanced BST? That is if the insertion order was 1, 2, 3, 4, 5, 6, 7. Because if you insert 1, then it becomes the root. If you insert 2, it gets inserted to the right. If you insert 3, it gets inserted to the right, and so on. Right? So it's very unbalanced. So the worst thing that you could do is if you actually insert the minimum as the first, or if you also insert the maximum as the last, and then do it in the descending order. So if you also have 7, 6, 5, 4, and so on. So if you have 7 here as the root, then you insert 6, and then you insert 5, and so on. So that's also very unbalanced, but in the opposite direction, right? It's very heavy on the left. This one is heavy on the right. Okay, so our the height of the tree could range from log of n to O of n, depending on how balanced your tree is. Okay, so if you have the full binary tree, the height is O of log n. If it's very unbalanced, the height is O of n. And so since we have our methods run in O of h, our worst case running time could be between log of n and O of n. Okay, depending on the balance. So the running time actually depends on the tree structure or the balance of the tree. Okay, so we just said that it's O of h, but the height depends on the structure of the tree. Okay, so to summarize what we've seen, what we've discussed so far for binary search trees, so the BST should follow this property, right? The order property. So all the keys to the left should be less than the key of the node, and then all the keys to the right should be greater than the keys of the node. And it's not just the left child and right child, it should be the whole subtree. Left subtree, right subtree. Okay? And then search, insert, and delete runs in O of h, which is the height, because search is the bottleneck. And if you have a balanced tree, the height is log of n, which is good. That's what we want. But if it's unbalanced, the height is O of n, which is bad. It's not what we want. So since we said that the earlier search, insert, and delete runs in O of log n, is there a way to keep our BSTs balanced so that we can claim that search, insert, and delete actually runs in O of log n? Okay, so can we make our BSTs balanced? Well, in fact, yes. So that is the purpose of the balanced search trees, which we'll discuss for the rest of the lecture. Okay, so you have the Splay Trees, the AVL trees, the red-black trees, and the 2-4 trees. So all of this trees here is the aim of these trees is to attain some kind of balance, so that we are close to the O of log n time compared to the O of n time if you have an unbalanced tree. Okay, so we'll take a look at each balanced search tree, starting with Splay tree. Okay, but before that, we'll actually need to discuss a concept first called rotations, because rotations will be used in the balanced search trees. So what are rotations? So you do a rotation when you rotate a child node to be above the parent. Okay, so you do a restructuring by rotating the child so that it becomes above the parent, so it becomes the parent now, and then the parent earlier becomes the child of the node. Okay, and the goal of doing rotation is to fix an imbalance on one side. Okay, so as we'll see in the next slide, and by doing rotations, you restructure the tree, so you rearrange the nodes. But even if you restructure the tree, you must always keep the BST property. Okay, that the left must be less than the node, then node is less than the right. Okay, so you should not violate the BST property after restructuring, so it should have the same in order traversal before and after the rotation. Okay, so yeah, it should not break the BST. So these are the rotations that we can do. So we have 4. So you have the right rotation, the left rotation, and then the double left right and right left. So these are the single rotations right here, and then these are the double rotations. So let's take a look at each one. So the right rotation happens when you have this pattern. Okay, so for the rest of the discussion, you will need to be able to identify patterns of the node's structure, or the structure of the node and the parent, and possibly the grandparent also. Okay, so try to follow the patterns, and then when you identify them in the actual trees, then that's when you know that I have to apply this particular rotation because it's this pattern. Okay, so for this one, this is a right rotation because this is a left imbalance. So the node that we're going to rotate is the node 2, because node 2 has a left imbalance, right? So it's heavy on the left, right? Because it has an extra node here, and then the triangles here are just subtrees, right? So that could be anything. It could be nodes, it could just be a null node, it doesn't matter. Okay, but the one thing that we notice is that it's left heavy here. So what we can do is we can do a right rotation. So we'll rotate this node to the right. Okay, so it becomes like this actually. So it becomes the parent, and then the parent becomes the child here. So after the right rotation, 2 becomes the parent, 3 becomes the right child of 2, and then 1 is still the same. And then you'll notice I also colored a subtree here yellow because everything else stayed the same, right? 1 still has A and B, 3 still has D as its right child, but this C here changed. So from being the right child of 2, okay, it changed and became the left child of 3. Okay, why is that? Because 2's right child became 3, so we can't have C here anymore. So we have to find a place for C, and that is on the left child of 3, because the old left child of C of 3, which was 2, now became its parent, so that is safe to insert there. Okay, and yeah, so that's what you need to notice, that the C here transferred to here, okay, after the right rotation. Okay, so it still makes sense to transfer it here, because C at this point, before the rotation, C is, it's greater than 2, right? C is greater than 2 because it's in the right of 2, but it's less than 3 because it's in the left subtree of 3, right? After the rotation, C is still greater than 2 because it's in the right subtree of 2 right here, but it's still less than 3 because it's in the left subtree of 3. Okay, so it still follows these conditions here. We just reattached it somewhere that it would fit in. Okay, so if you have a left imbalance on this node, you can do a right rotation. So to counter a left imbalance, do a right rotation. Okay, now if you understood that, then it should be easy to understand left rotation. It's just the opposite, right? It's just the symmetric version of the right rotation. So this time you have a right imbalance. So 2 is the node that you want to rotate because it has a right imbalance. So it's right heavy because of the extra 3 here. So to fix this, you want to do a left rotation wherein 2 becomes the parent and then 1 becomes the child. So 2 becomes the parent here, 1 becomes the child, and then 3 is still the right child of 2. And then the one thing that became updated was the B sub 3 here. Okay, so similar to what we had in the previous slide, it became the left child of 1 here. Okay, so yeah, that's also the pattern. So that's just a single rotation. Okay, if it's a left imbalance, do a right rotation. If it's a right imbalance, do a left rotation. So the opposite direction. Okay, now how about the double rotations? So this one is called a right left rotation, and we do this if the pattern looks like this. So if 2 is what you need to rotate and it has this pattern, so it looks like an angle, right? So to do that, so first this is a left imbalance on 2 because it's kind of heavier on this side, right? So we need to do a right rotation first. So that's why it's called a right left rotation, because you do a right rotation first. So when you do a right rotation on 2, then 2 becomes the parent and 3 becomes the child, and then C here becomes 3 attached to 3, just like what we did earlier. And then after that, this already looks like the one for left rotation for 2. So we can do a left rotate here where 2 becomes the parent and 1 becomes the child. Okay, so it's a left right imbalance because earlier it was a left imbalance on 2 right here, and then on the second part it's a right imbalance on 2 because it's right heavy here. Okay, that's why we needed to do a left rotation. Okay, so if it follows this pattern, do a right left rotation. Now if you understand this one, then it's easy to understand the left right rotation, because again it's just the symmetric version of right left. So it's just a counter. Okay, so again 2 is at the bottom and it's it has a right imbalance here because it's heavier on the right side, right, for 1. So we'll do a left rotation to counter that. So if you do a left rotation, 2 becomes the parent, 1 becomes the child, and then B becomes transferred here. And then after doing this, then we can do the right rotation for 2, wherein 2 becomes the parent now. So we have now balanced the tree from looking like this to looking like this, which is what we want. Okay, so yeah, those are the 4 rotations. So you have the right, left, left, right, and right, left. Okay, now what would have happened if you used the wrong rotation? Okay, so earlier what if we see we want to do 2, right? But then this is, you can say maybe this is left heavy because everything is on the left, right? There's more nodes to the left. So if it's left heavy, maybe I can just do a right rotate to counter this. Okay, what will happen if you just do a right rotate instead of a left right rotate? Because you'll notice that this one should follow the left right rotation, right? Because it has this shape. So if you did just a right rotate because you feel that is left imbalanced, like direction are right, then if we let this sub 3 here become E, the E sub 3, okay, which will just substitute it to keep the 3 simpler, and then we'll do a right rotate here. If we do a right rotate, then 1 becomes the parent, 3 becomes the child, and then if we plug E back in, that's 2 and the BC, then it will look like this. Well, this is still imbalanced, right? So you went from an imbalance that looks like this to an imbalance that looks like this. So you did not really fix anything. Okay, so that is why it's important to use the correct rotation pattern. If you see the pattern that it belongs to. Okay, so if you see this pattern, like this one, do a right rotate. Okay, like that. Oh. So if it's this pattern, do a right rotate. If it's this pattern, do a left rotate. If it's this pattern, like that, then do a left rotate first, and then a right rotate here. And then if it's this pattern, do a right rotate first before doing a left rotate. Okay, so follow the patterns for rotation. Okay, so please make sure that you understand these 4 rotations, because these are foundational steps in the rest of the balanced search trees. So the other balanced search trees will be using this rotation as basis or as operations. So if you don't understand how this works, then it would be very difficult for you to grasp the other balanced search trees. So please try to make sure that you understand this one first before moving on to the latter part. Okay, so you'll also notice that we said that before the rotation and after the rotation, the in order traversal should not change, right? So it should be the same. So you have for the after version, you have A1B, and then the root is 2, and then C3D. So that is the in order traversal, A1B to C3D. Okay, so for the before, so we'll do the left sub 3 first. So that's A1 and then B, and then the root here is 2, and then the right is C, and then root is 3, and then the right is D. So it's still the same, right? So it did not change. For this one, it's still A1, and then the right sub 3 is B to C, and then the root is 3, and then the right sub 3 is D. So it still follows this traversal. For this one, it's A1, and then for the right sub 3, it's B2 C3D. So it's still the same. And then finally, this one is A1 B2 C3D. So that is the in order traversals for the before and after, which should stay the same, because we're just restructuring the tree. We're not violating the BST property. Okay, so you can go ahead and confirm for yourself, but the rotation should have the same in order traversal before and after the rotations. Okay, so those are rotations. So again, please make sure that you understand these concepts first before proceeding with the rest of the balanced search trees, because you will need to understand this to understand the rest of the discussion. Okay, so those are rotations. So let's now look at our first balanced search tree, which is the Splay tree. Okay, and the basic idea is you have the node here, you'll splay it to the root. Okay, so what do we mean by that? Okay, so for the Splay trees, so as quick background, it was created in 1985 by Daniel Sleeter and Robert Tarjan, and A splay tree is basically a self-adjusting binary search tree. Okay, so what do you mean by self-adjusting? So every time that you do a search, insertion, or deletion, it will modify itself. Okay, so it will adjust itself. And it does so by doing the so-called splay operation. So the splay operation will move the recently accessed node to the root. Okay, so if you search for a node, after searching, you move that node to the root. If you insert, move that node to the root, and so on. Okay, so and by moving it to the root, you're also following the BST orders. You're not violating anything. Okay, so why do we want to splay nodes or recently accessed nodes to the root? So if the frequently accessed items are near the root, then we can reduce the search times when we access them again. Okay, so for example, if you insert 32, so when you insert it, you splay it to the root, and then when you search for 32, it's faster because it's already at the root. Okay, or if it was brought down by another splay operation, at least it's near the root. Okay, so you can reduce the search time for that. And this splay tree follows the so-called Pareto principle, or also known as the 80-20 rule. So maybe you've heard of this before. So the 80-20 rule states that 80% of the results only come from 20% of the actions. So meaning most of the outcomes are only caused by 20% of the possible causes, right? So bringing that into the context of splay trees and searching, so 80% of the access, or 80% of the items that you actually operate on, so the search method, the search operations, the insert, the deletions, 80% of those operations are actually only to 20% of the items. So there's a set of items that you frequently access, and your operations kind of revolve on those frequently accessed items. So if they are frequently accessed, then it makes sense to put them near the root, so that if you search for them or you delete them, then your operation will not take as long because it's already near the root. Okay, so an example application of splay trees would be for caching, right? So if you're familiar with caching, it's saving the recently accessed maybe page, like the cache in the browser, so that if you access it again, you don't have to reload it, but you can just access it from the cache, right? So if it's a frequently accessed item, it makes sense to put it at the front so that it's easier to access it again. Okay, so that's the concept of splay trees. Okay, so let's see how to do search, insert, and delete. But I've basically alluded to it earlier already. So after search, splay the node. So to search for the key K, we'll do a normal BST search because splay trees are still BSTs, and then so we'll have the search for K, and then we get a node, right? So this node is either a binary tree node or a null node. So if it's a binary tree node, it means that we've found it, right? If it's a null node, it means that we didn't find it because we were given a null node back. Okay, so if it was found, so we will splay that node that was found to the root through a sequence of rotations. Okay, so we'll bring this node that was found to the root by splaying. But if it's not found, we will splay the null node's parent. Okay, so if it was not found, diba, we return the null node. So the parent of that null node, that is what we will splay. Okay, so I'll show you that in an example later. And the reason for this again is if we want to search for the key K again, at least it's already at the root or near the root. Okay, if it was overtaken by other splay operations. Okay, so it makes it faster. So how do you actually splay? So we said that we want to bring this node to the root through a series of rotations, but how do you actually do it? Okay, so for splaying, you first need to identify two things. First, you ask the node, is the node a left child or a right child? Okay, then you check the parent of the node. Is the parent a left child or a right child of the grandparent, or is the parent already the root, meaning it doesn't have any parent anymore. Okay, so you identify these two things, the uh, the node and the parent. Is it a left child, a right child, or the root already? And identify the pattern, and then do the rotations according to the pattern. So there will also be 3 patterns here for splaying, and I'll show you that in a while. And then once you've identified the correct pattern, then you do the rotation that is appropriate for that pattern, and then we'll repeatedly do this until the node that we're splaying becomes the root. Okay, so once it reaches the top, then we'll stop. Okay, so that is the basis for splaying. So what are these splaying patterns? Okay, so we have 3. Okay, so earlier I said that we have to take note of the parent and the node. So the node, I will call it S, because that means that it's a splay node. The parent, I'll call it P, and then the grandparent, I'll call it G. Okay, so we have 3 sets of patterns here. This one is called the zigzag pattern because it has a zigzag. So it's like this. So it's either like this or like that. Okay, the next one is called the zig-zig pattern because it follows the same direction. So it has either left child, or a right child. This one is a left child, right child, and then this one is a right child, left child. So it's opposite. That's why there's an angle. So it's a zigzag. This one is the same direction, so it's a zig-zig. And then for the third one, it's just one operation, like either left child or the right child of the root. So if it's already the root, then we only do one operation, one rotate. So it's just a zig. So it's either zig left or zig right. Okay, so those are the 3 patterns. So it's pretty simple. It's either an angle, a straight line, or just one line because it's just the root. Okay, so let's take a look at each pattern more closely. Starting with the zigzag pattern. So for the zigzag pattern, you apply this if the node is the right child of a left child, or the left child of a right child. So how does that look like? So if the node, the splay node, is the right child of a left child, or the node is a left child of a right child. So the parent is a right child of the grandparent. Okay, so it creates an angle basically. Okay, it's not a straight line. So what do you need to do when you encounter the zigzag pattern? Then the node and the parent are in different directions. So what you'll do here is you'll just rotate the node twice, and you'll rotate it to the opposite direction of the So here in the first one, the node, the display node is the right child. Okay, so what you'll do is you'll rotate left. Okay, so you rotate left first. So after rotating left, it will look like this, right? So the S will be above the parent now. And then since S now is the left child, then we'll do a right rotation. Okay, so that's why it's rotate LR. Okay, but you're doing the rotation on the splay node both times. Okay, and then for the other side, if it look like this, the splay node here at the bottom is the left child of the parent, right? So if it's a left child, then we'll do our right rotate on the splay node. So after right rotate, which is this one, it looks like this. And then since the splay node is now the right child of the grandparent, then we'll do a left rotate, which is this one. So you rotate left right or right left depending on the direction. So you always rotate to the opposite side of where it is heavy. Okay, so yeah, so that is the zigzag pattern. Okay, so Let's see. So let's see that in an example. What if we search for 19? So in our search for 19, it will find it in this node, right? And identifying this pattern, it's a zigzag, right? Because it's an angle. So we'll first rotate 19 with a what? So it's a right child, so we'll do a left rotate. Sorry. So left rotate will look like this. And then now it's a left child, so we'll do a right rotate, so it will look like this. So this is the final splay tree after searching for 19. So 19 is now at the root node, and you can see that it's somehow kind of balanced. Okay. Now how about if we search for 41? This time it's the opposite zigzag, but still a zigzag nonetheless. So 41, you can see that it's a zigzag. So since it's a left child, you'll do a right rotate. Okay, so right rotate that, and then 41 is now a right child, so you'll do a left rotate. So if you left rotate that, it will look like this. So this is the final splay tree. So for this one, it's not really balanced, but you did put 41 at the root, which is the purpose of splay trees. So you'll notice that with splay trees, it's not always balanced, but the recently accessed item is always splayed to the root. Okay, so that is the zigzag. Now how about the zig-zig pattern? So for the zig-zig, you do this if the node is the left child of a left child or the right child of a right child. Okay, so how does that look like? So it's either left child of a left child, so that's the S, or the right child of a right child, like this. Okay, so the node and the parent are in the same direction. That's why it's zig-zig. Okay, so what do you need to do in this case? For this one, you can just first you need to rotate the parent and then rotate the node, but both of them will be in the same direction because they're in the same direction anyway, right? So first here, since this is left heavy, then we'll do right rotations here, right? So rotate R here. So first we'll rotate the parent, so we'll do a right rotation on the parent, so that brings the parent on top, the grandparent as the child, and then we'll rotate the node again with the right rotation, so we have the S here. So it's not really balanced, but at least we placed the splay node all the way to the root. Okay, and then for the opposite, it's more or less the same, but this time we'll do left rotation. So do the rotation on the parent first. So left rotate, it becomes like this, and then left rotate the splay node, becomes like this. Okay, so the purpose is to bring the splay node to the root. Okay, so yeah, rotate. So unlike zigzag, wherein it was both the node, it was rotating the nodes both times. Here you need to rotate the parent first and then rotate the node, because they need to be rotated on the same side. Okay, so that's the zig-zag. So let's see an example. If we search for 1, we find it here. So you'll identify that pattern as a zig-zag because it's left heavy both times. So what we'll do is we'll rotate 10 first, rotate that to the right, so it becomes the root, and then we'll rotate 1 to the right also. So now 1 is at the root after splaying. Okay, it becomes super imbalanced, but the purpose of splay trees is to always bring the recently accessed node to the root anyway. So we have accomplished that. Now how about if we search for 60? So it's still zig-zag, but it's on the opposite direction. So first we'll have to rotate 55 to the left, which is the parent node. So rotate left, and then rotate 60 to the left also. So rotate left will produce this one, and this is the final splay tree. So again, we had a very unbalanced tree, because when we searched for 1, that was the minimum key, and then when we searched for 60, this was the maximum key. So that's what happens when you have the min or the max as the root, right? It becomes very unbalanced, right? But yeah, that's the zig-zag. Finally, the last pattern is called the zig pattern. So you do this when the node is the left child of the root or the right child of the root. So if the parent is already the root, then you only need to do one rotation, because after that one rotation, the node will become the root anyway. Okay, so only one rotation needed. So you rotate the node left or right depending on the direction. So if it's a left child, then you do a right rotate. If it's a right child, then you do a left rotate. So always the opposite. Okay, so I won't show you the example anymore because you've already seen this in the basic left and right rotation. Okay, so that's the zig pattern. So let's try to search for 10 in the example. So it's here, and since 10 is already the child, the left child of the root node, then we can just do a zig to the right. So if we rotate that, then it becomes like this. That's already the final splay tree because 10 is already at the root. Okay, so to summarize, this is the table that tells you when to zigzag. So if you have the left child of the right child, left child of a right child, or right child of a left child, then you zigzag. So that is when the directions of the node and parent are different. Okay, and you rotate the node both times. So depending on the direction, you do the opposite rotation. And for zig-zag, it's always the node and parent are in both directions. So first you rotate the parent and then you rotate the node. Okay, to opposite to the side of where the node and parent are directed. And then for the zig, you do that if your parent is the root. So you do the opposite rotation. If it's a left child, rotate right, and vice versa. Okay, so this is the summary of the three patterns for splaying: zigzag, zig-zag, and zig. So again, try to make sure that you can understand and can recognize when to do the following patterns and what to do on that pattern, so that you can understand how to do splaying in Splay Trees, because search, insert, and delete will do splaying all the time, okay, in Splay Trees. Okay, so yeah, make sure that you understand these concepts first. So if we try to put all of those three things together and we search for 69, well, 69 is not found, but we'll stop at 55, because at 55, if it tries to go right, there's nothing there. So that is where 69 is supposed to be. So we said earlier that if it's not found, then you splay the parent. So 55 is the parent of the null node, so we'll splay 55. Okay, so what pattern is this? This is just a zig pattern, right? Because it's already the right child of the root node. So we'll just rotate 55 to the left, and this will become the resulting tree. So this is the final splay tree after searching for 69. You splayed 55 because 69 was not found. So the reason for splaying 55 is if you want to search for 69 again, then at 55, if you go to the right, then you can already say that 69 is not found. Okay, so it's faster because the parent of where you stop was played also. Okay, now how about if we search for 12, and this time 12 is actually in the tree, right? So searching for 12 will give us this path, right here. So we found 12 all the way at the bottom. So let's try to figure out the first pattern. The first pattern is a zig-zag, right? Because it's a left child of a left child. So if you do a zig-zag, then you rotate the parent first, 16. So rotate to the opposite direction, rotate to the right. It will look like this. And then rotate the child, the splay node, which is 12. Rotate this also to the right, so it will look like this. Now after that, for 12, what is the next pattern? So 12 is here, right? So that's what we need to splay. So we'll identify the next pattern, which is this one. So that is a zigzag, right? So a zigzag pattern. So we'll need to rotate 12 to the left first, so like this, and then to the right, like that. And now 12 is at the root node, so we'll stop here, and that's the final splay tree after searching for 12. So 12 is now at the root. Okay? One last example. What if we search for 16? For 16, we found it here. So the first pattern is a zigzag, right? So it's a zigzag right here. So we'll first rotate 16 to the right, like this, and then to the left, like that. And then after that, 16 is already the left child of the root, so it's just a zig pattern. So we'll rotate it to the right, and then it will look like this. Okay, so that's the final splay tree after searching for 16, and it kind of looks balanced somehow. Yep. So that is Splay Search. Okay. Now, how about insertion for splay trees? So for insertion, it's pretty simple. If you want to insert the key K and value V, do the normal insertion for BST, just like what we did earlier, and then splay that newly inserted node to the root. Okay, so it's basically the same thing. Once you insert it, you just play that node to the root. So let's see an example. If we insert 23, where should we insert it? So it should be here, right? So 23 is less than 32, so go left. Greater than 10, so go right. Greater than 19, so go right as well. So this should be where 23 will be inserted, right? So let's check if we are correct. It should be, oh, there. Yeah, so it's there. So it's inserted in that position, but then we have to splay it. So when we splay 23, what is the first pattern? This is a zig-zig, right? It's this one. That's a zig-zig pattern. So we will rotate the parent first, 19. So rotate it to the left, so it will look like this, and then rotate 23 to the left also, so it will look like this. So now 23 is at the top, but it's not the root yet. So the next pattern is a zig because the parent is already the root. So we'll just do a right rotate here, and then that's already the final splay tree after splaying 23 to the root after inserting it. Okay? Yeah. So that's insert. It's pretty simple. Finally, when we do delete, so when we delete the key K, we'll also do the normal BST deletion. Okay? And the deleted node could be one of two things. It could either have the key K itself, right? If it's either case 1 or case 2, or the deleted node is not the one that contains key K, but it's the next node if it encounters case 3. Okay, but either way, we delete something, right? So it's either the exact node that has the key or the next node. So what will we splay after deletion? Because once we delete that, we cannot splay it anymore because it doesn't exist in the tree anymore. So what we will splay is the deleted node's parent. Okay, so whatever the deleted node was, splay its parent to the root. Okay, so let's see that in an example. So when we delete 97, when we search for 97, it's found here, right? So you can find 97 here. So we can delete this one, because this would be what? Case 1, case 2, or case 3? This is case 2 because it has one child, which is 93. So 93 will just replace 97 here, right? So 93 would replace it here. But what is the parent node of the deleted node? That would be 88. Okay? So we will splay 88. Okay? So when we splay 88, well, it's just simple now because it's near the root. So its parent is the root, so it's just a zig operation. So we'll just do a left rotation, and then that's the new splay tree. Now you'll notice the whole 65 subtree here was transferred, right? The whole 65 subtree will become the right subtree of 44. So if we go to the next slide, becomes the right subtree of 44 because we moved this whole subtree after rotating. Okay, so yeah, so even if we deleted 97, because obviously 97 would not be in the tree anymore. So we splayed the parent of the deleted node, which was 88. Okay. Now let's see one more example. Okay, so this is the final splay tree. Now how about if we delete 44, which is actually the root node? So if we delete 44, if we follow the example from earlier, this would be case 3, right? Because it has 2 children. So if we look for the next node, that would be 44 would go to the right once and then go left. So keep going left until we find the next node, which is 54. So we'll replace 44 with 54. Okay, so we found the next node, we'll replace it with 54, and then we'll delete this. And it's easy to delete because it doesn't have any children, so that's a simple delete. And the parent of that would be 65, so we will splay 65. So from 65, what is this pattern? This would be a zigzag, right? Because that is a left child of a right child. So with the zigzag, we will rotate this to the right there, and then rotate it to the left. So now it becomes the root. Okay, so after deleting 44, you splayed 65, which is the parent. Okay, so for splay trees, the rotations are not actually for balancing, but to bring the splay node to the root. Okay, but even if we're not explicitly balancing it, by splaying, we're doing a restructuring of the tree, and in effect, we're actually rebalancing the tree indirectly. Okay, sometimes it's not a perfect balancing, because like what we saw when we had the min and the max as the root, it was perfectly imbalanced, leaning heavily to one side. But in most cases, splaying will kind of rebalance the tree even if it's not perfect. Okay, so it's not strictly balanced, and that makes it easier to implement compared to the other balanced search trees like the AVL or the red-black trees, which we'll discuss later. So it's easier to implement because it's not strictly balanced. It just wants to bring the node, the splay node, to the root. Okay, so it's just semi-balanced, but it still has a fast running time. So even if the fast running time comes from the fact that the frequently accessed nodes are near the root. Okay, the fast running time is not because it's balanced, it's because the frequently accessed nodes are near the root. So your search will not go deep into the tree, it will be shallow. Okay, so the average running time is still O of log n, but in the worst case it's still O of n, because when you have a very unbalanced tree, which happens rarely in splay trees, then you still get O of n, but in average case it's still O of log n. Okay, because your searching will be shallow, it's near the root because the frequently accessed items are there. Okay, so that is splay trees. Okay, so to summarize, when should you splay? In search, when you find the node, then you splay that node. If you don't find the node, then you splay the parent of the null node, so where you got stuck basically. Okay, for insert, you splay the newly inserted node, and for delete, you splay the parent of the deleted node, because obviously you can't splay the deleted node, it's not there anymore, so you splay the parent. Okay, so you splay each time you search, insert, and delete until the node reaches the root. Okay, so that is the splay trees. You want to go to the root. Okay, so yeah, that's it.